Hess's law. Another feature of enthalpy is that it is a state function. In general, for a state function, the path taken between initial and final states does not matter. Only the initial and final states are important. The enthalpy change in going from some initial set of reactants to a specific set of products is the same, no matter what route is taken to get from the reactants to the products. Hess's law takes advantage of the state function nature of enthalpy to provide an alternate way of calculating the enthalpy of reaction. Consider the combustion of hydrogen gas to give liquid water. That delta H is minus 285.8 kilojoules. We can think of that as happening in two steps. One, we combust the hydrogen, with oxygen of course, to give water vapor, water in the gaseous form. That delta H is minus 241.8 kilojoules. Then, step 2, we'll condense the gaseous water to liquid water. That delta H is minus 44.0 kilojoules. Steps 1 and 2, 2 and 1 here, add up to the original reaction. The sum of those enthalpy changes equals the enthalpy change of the overall reaction, minus 285.8 kilojoules. This illustrates how reaction equations can be summed to get a new reaction equation. The enthalpy change for the new reaction is the sum of the enthalpy changes for each individual reaction. Or, if reaction A is the sum of two or more reactions B and C, then the enthalpy change for reaction A is the sum of the individual enthalpy changes of B and C, right here. That's from the conservation of energy. It works even when an overall reaction does not occur by way of the individual reactions. We've discussed obtaining enthalpy changes for certain reactions using calorimetry. However, for many reactions that can't be done. For instance, the enthalpy change of converting graphite to diamond, which are both forms of carbon, cannot be determined directly since it is not practical to do this in a laboratory, unless you're Superman or Superwoman. Hess's law is used to calculate enthalpy changes for such reactions by composing the reaction of other reactions which can be done. We want the change in enthalpy for graphite turning into diamond. We don't have that. We can't do that in the lab. But we have the enthalpy change for graphite plus oxygen forming CO2. And that's delta H is minus 394 kilojoules. We'll call that equation 1. We also have diamond combusting to form carbon dioxide, and that has a delta H of minus 396 joules. Call that equation 2. Now we want to come up with this equation right here. One way of doing that is take reaction 1 as is, and then reverse reaction 2 and add them together. Try that first before going on. So even though the conversion of graphite to diamond cannot occur through those reactions, we can still manipulate the equations to determine the enthalpy change. We bring over equation 1 as is, but we're going to reverse equation 2 to become equation 3. And since we do that, we have to change the sign of the enthalpy. Now let's look if we add those equations together. You have CO2 on this side on this equation, CO2 on this side, so they'll cancel out. We have O2 on the right, O2 on the left, also cancels out. And what are we left with? Just the graphite turning into diamond. And that's right over here. The enthalpy change is now we add those two numbers. Here's for equation 1, and here's for equation 3, which is equation 2 with the negative sign out of it, right? We reversed it from negative to positive. So we have negative 394 plus 396, and we get a change in enthalpy of 2 kilojoules.